problem number 1, we're going to determine if the equation is exact, and if it is, then we're going to solve for it, okay? So this thing here is our p of xy, and this q of xy is the thing in front of the dy. Okay, so we have those two, and in order to determine if our equation is exact or not, we have to determine whether the partial of p with respect to y is equal to the partial of q with respect to x, okay? And so let's take the partial with respect to y of this thing, and that would just give us a 1, right? And then as is the partial of this with respect to x, that's also a 1. So our equation is exact, so equation is exact. So that means we're going to solve for it, okay? And we can solve pretty easily. So let's do so in this little blank space here. So we have our p of xy, which is supposed to equal partial of f with respect to x, and it is because our equation is exact, okay? And this is equal to 2x plus y. So we're going to integrate with respect to x on both sides, integrate with respect to x. So we get one of our candidate functions is f of xy is equal to x squared plus xy plus, it could be like a random function, a random single variable function of y, okay? And then let's see, if we go from the q side, then this is equal to the partial of f with respect to y, which is equal to x minus x minus 6y. That is, I need to work on my 6's. But anyways, yeah, and then if we integrate with respect to y on both sides, we get another candidate function, which is f of xy is equal to xy minus 3 times y squared, plus it could be another function just of x, okay? So we do see that we have a function just of x here, so this is equal to our x squared, and our function just of y is this thing. So we're just going to fill in the gaps here. So this is our this is negative 3y squared. So when we put it all together, we get the answer, and I'll write that on the next slide. So our answer for this problem is going to be f of xy is equal to x squared, and then plus our xy minus a 3y squared, and this is equal to some constant, okay? And this is the solution to our ODE.